we are in Canvas. Couple of things I want to remind you guys of. In Canvas, there's this to-do list. I wouldn't use that to like navigate things for you to do, like if you're missing assignments or things like that. The best place in the navigation to look at what to do in the order it was assigned was just to go to modules, right? And this is just a brief overview because I know some students are trying to make up work and get things turned in. The most current week that we're on, right, week 12 is going to show up at the top here. You scroll back down, we go to week 11, week 10, and so on and so forth. As you can see, I'm in a student view right now, so this is the test student. On the assignments that are past due or have not been turned in, there's a little red mark over here. It says this assignment is overdue. All right. So if the assignment hasn't been turned in and it's past the due date, you're going to get a little mark next to it showing that it hasn't been submitted. So you can use that as kind of a guide marker as you go back through the weeks to see which things you may want to do. So keep those things in mind. Also, the discussion boards I use, while they're worth, I think I have them at 15% of your grade, the self-assessments are worth a larger proportion of your grade, right? So getting those turned in can have a larger impact on your grade than getting, you know, a bunch of discussion boards turned in, right? The discussion boards are going to help your grade, right? Because those are the easiest things to get points on. You know, if you do them, you'll get credit, right? As long as you've attempted to answer the question in some way. So those can help add to your grade. But if you're missing the self-assessments, those are going to hurt your grade the most. So making those up will make the biggest change in your grade, especially if you're trying to move towards passing the course. Okay, so I would look at these, you know, the self-assessments. They have the green checkbox next to them. Those are the most heavily weighted assignments we have. As of now, there's only 2 of them, right? We'll have at least 1 more, possibly 2 more within this unit. All right. So those things are going to be important. Getting those self-assessments turned in, even if they're not perfect, right, is better than a 0 for not doing it all. All right. So there's that. You can also look at your grades. I have this option open for you guys within Canvas, right? This will obviously also show you which things you are missing, right? It actually says missing. If you've been excused from an assignment, right, it'll say X, EX, right? So this is another way to kind of go through and see things that you're missing and what your grade is at, right? It also shows you the grade breakdown, what things are worth. All right, I have built-in extra credit. If you go back and do some of these practice things that I removed from what you guys had to do from the beginning of the semester because there's too many things, that can act as extra credit. Okay, so if you're looking for extra credit, that's how to get some. You can change how this is arranged. I have it. You can do due date, assignment group, module, title, and it'll go alphabetical. That's up to you. You can also, as it says here, click to test a different score. You can check and see what scores will do to your grade. All right. So there's that. Okay. And yeah, that's kind of the most that you'll need to do for navigation and finding things that you may want to make up, things that you're missing, how to check your grade, right? The grade in Canvas here is the most current up-to-date grade, right? Synergy only gets updated for progress reports and report cards for me. Some teachers are using it more. I just put in the progress report and report card grades for that. All right, so this is where you want to look for your most current grade. Okay. Are there any questions about Canvas, where to find it, missing assignments, anything like that? So then again, we are in week 12. This is we have our second self-assessment here, unit 3, linear function self-assessment. There's a demonstration of understanding in there. It is 4 parts of a question. It's not too involved. I think the easiest way to get it done is to just do it on paper by hand, take a picture and upload the picture. Trying to get the text editor to type everything out that you want could be a little difficult. That's just my suggestion as far as the easiest way to do it, as far as doing the work and submitting it. We will have a discussion board for today that you can do after class. We're continuing with exponential growth today. We're going to look at a couple more examples, kind of develop that idea a little bit more. I'll go over the discussion board at the end of class after the lesson because it'll make a little more sense after that. Yeah, other than that, those are the only 2 assignments that have been added this week. We have the self-assessment and this discussion board. We have our live class resources from Tuesday's class. Those are all updated. We have our class recordings and the notes available here for period 2. There you go. All right. So you have that. And then today's live class resources will be updated after class today once I have those things ready, because they get prepared during class. Okay. Any questions about this week, week 12? All right. Then we shall move into the lesson. Alrighty. So, as usual, if you have any questions, something doesn't make sense, you need me to slow down, you need me to do say a better example of something or explain something in a different way, please let me know. Just put it in the chat, unmute your mic and say so, raise your hand. Any of those things will work. And we're going to get started. It is Friday, November 13th, 2020. We are continuing with our look into exponential growth. Today we're going to look at what happens when you change the rate of change or the start value in a exponential growth scenario. All right, so real quick, we'll review what we did last class. All right, we looked at this pay it forward example as an introduction to exponential growth. All right, we saw the tree graph that showed how we start with one person, they do 3 good deeds, right? And then we have 3 people at that stage. Each one of those people does their good deeds. We got 9 people, they all do good deeds. We got 27, and it continues to grow. We have the tree graph as a visual representation that shows that growth, and we can visually see it expanding and getting larger. All right. We looked at the table in which you guys calculated the remaining values after the second stage here. We had 27, 81, 243, 729, 2,187. And we determined that we were able to calculate the next number of good deeds by multiplying whatever number we already had by 3 to get to the next one. 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, and so on. So multiplying by 3 became our rate of change to get from one value to the next value. All right, and this is different than what we saw in the previous unit about linear functions, where our rate of change was a constant addition of a number, rather than now we're looking at a constant multiplication of a number. We also took a look at the graph. Right? This graph shows how, as we move along on the x-axis in the stage of the process or the level of the process, the number of good deeds starts to grow faster and faster. Right? And this line is an exponential curve, as we would call it in math. It is not a straight line. it definitely turns, and it has a curve to it, right? Which is visually much different than the linear functions we previously studied, that are just a flat straight line, no curve. And then we have the symbolic rule and now next rule for this scenario. In this case, we have y equals 1 times 3 to the x, or now times 3 equals next starting at 1. All right. And with these, it's good to point out that just like in a linear function, we have our start value, our rate of change, right, and our variable that represents something. The same thing occurs with this new exponential function, the symbolic rule, right? The 1 here, right, that is our start value, right? Just like in a linear function, we see that in the table as the number that goes along with 0 in the process, right? The y-intercept, where x equals 0, right? That is our start value. In this case, it's how many people we started with in the process, right? Then we have the rate of change, which in this case is 3, right? And we see that as that number that we multiply by each time to get from one number to the next. Right? So a lot of these same things, these same ideas that we used in the previous unit are still here, right? They just have a slightly different look to them because instead of adding, we're multiplying. That is basically the only difference, right? In a linear function, if this was adding 3, we would just have a plus sign between the 1 and the 3x, right? And instead of x being the exponent, the x would just be right next to the 3. Right? So we've just adjusted things to account for multiplication instead of addition, right? So when we do put numbers right next to each other and one of them is in parentheses, right, that implies multiplying. Okay. And lastly, this x, right, our variable here, it can represent the stage in the process, which helps if I can spell. Right. It's the stage. It could be time periods, as we'll see in another example today. Right. It's whatever our unit is. In this case, it's the stage, right? The stage of the process. It could be number of hours. It could be number of days. It could be number of repetitions. Just it all depends on the context on what x is holding the place for. All right. And again, these same values show up in our now next rule. This 3 is obviously the rate of change. And the 1 is our start value. And in a now next rule, there is no variable. We don't have to worry about an x or a y or anything like that. We're just saying the process. Now times 3 equals next starting with 1, or starting at 1. Okay. Any questions about these technically 5 different representations of an exponential function? Okay. Does anyone need a moment on this screen to write anything down if you're putting anything in your notes about this? Please raise your hand. So now we're going to look at another example about bacteria cells. Bacteria grows exponentially. Different bacteria grows at different rates. Suppose a scientist is researching a new strain of bacteria. She's curious about how the bacteria grows and sets up an experiment where she starts with one bacteria cell in a petri dish. You guys know what a petri dish is? Not that it's terribly important for the example, but just curious. No, all right. So have you ever seen like in a biology textbook or something like that, where they show like a scientist looking in a microscope and they've got this little circular dish and it's got like amber colored jelly in it? That's a petri dish. Let's see if we can find a picture. Let me find a picture. Here, let's use this. So these are petri dishes. There's these little circular dishes that biologists use to culture bacteria and things like that. The jelly that goes inside of them is like a nutrient-rich kind of thing that allows bacteria to populate and grow. And so they can monitor the growth of bacteria, how fast are they growing. They can also, like in this one, they're looking at mold, things like that. So that's what a petri dish is. It's just a little dish. It has some jelly inside of it, and that jelly allows different organisms, microscopic organisms, to grow and populate so that they can be studied. So there you go. Now we learned something. Boom. All right. Yeah, you've probably seen them. It just, the name probably isn't familiar. It's not, it's just like, it's a little dish, you know. So that one. All right. So again, they're looking at bacteria and they're starting. They use their super high-powered microscope. They picked out one bacteria and put it in the petri dish. They want to see how it's growing. Right? The scientist, she notices that every hour, when she checks on the dish, the amount of bacteria in the dish has doubled in size. Right? How can we model this growth with a tree graph, table, graph, and rules? Right? Rather than try to fit all that onto a slide here, we're going to jump over to OneNote to do the example because it allows me more space to work. So we have this set up over here. So we have the same example here, right? Same scenario. We want to know how can we model this growth with the tree graph, table, graph, and rules. So let us start with our tree graph. All right. So in this scenario here, we are starting, let's see, with one bacteria, right? That's important. Every hour, when they check on the dish, the amount of bacteria in the dish has doubled. As far as multiplication is concerned, what is doubling? What is that saying to do? What are we multiplying by? Yes, Jocelyn, thank you. Multiplying by 2. Yeah, thank you, Nicholas. Multiply by 2, right? So this right here says times 2. All right, awesome. And we have every hour, so that's our time period. And we start with one bacteria. I'm going to draw this tree graph going left to right rather than top to bottom. The direction in which it flows isn't terribly important. I'm doing left to right just so that it fits a little better. So I start with my one little bacteria here. And in 1 hour, this bacteria has split and doubled and become 2. Right, in the next hour, We double again. We now have 4 bacteria. Another hour passes, we get more. All right, and we can keep going here. We get 2 more, 2 more. Saving time by not drawing each line. All right, we're gonna stop there. So here's our little tree graph. It shows us that multiplying of 2. Okay, and so this first right here, right, our first guy here, that is times 0. Right, no time has passed. That's the initial bacteria. It's our starting point. Right, so then this next level in here is our time 1. Right, time is 2. Time is 3. And then time is 4. Right, so when we're looking at an exponential growth pattern, the initial part, the initial value there, right, it is at 0. Stage 0, time 0, level 0. And it gives us just the one guy. Right? And we can also look at our count now. Right, we start with 1. Right, and then we're at 2, 4, 8, 16. All right, and this again is following our pattern, right, of just multiplying by 2 each step along the way. Okay, so this is our little tree diagram, a tree graph. Again, it's visually, it allows us to see that growth. We can count if we need to. We can see the pattern a little more straightforward. All right. Now, yeah, so there, we've done tree graph. All right. So then we've done the tree graph up to this point. Might as well use that on our table, right? And again, it's important to recognize that we're dealing with hours. That is our measure of time. We could be doing chunks of time, like 30-minute time periods, in which case each level would represent 30 more minutes, right? But get into the exponent that we use counts the number of 30-minute time periods, not the total like hours. So there becomes a little manipulation of the calculation you have to do. We'll get to that. All right. So after 1 hour, we have 2. 2 hours is 4. 3 hours is 8. 4 hours is 16. Right, and we can continue. We have 32 and 64. Right. So we've now done up to 6 hours in the table. So the idea is that we're hopefully getting a good sense of the pattern, right? Multiplying by 2. So now we've got the tree graph, we've got the table. Let's make a graph. Did not space this out very well. Oh well. All right, so now on our graph here, we have our x-axis here, right? And we have our y-axis. I'm only showing the positive values for x and y because those are the only ones that apply to our problem. I'm not going to have a negative value for the amount of bacteria, and I'm not going to have a negative value for time because time travel up to this point is not possible. I cannot go backwards. All right. So this represents time in hours. Right. And this is, oh man, number of bacteria that worked out okay. Trying sideways. All right, so now we need to label some stuff. So we're at 0 on the corner. Go 1, 2, 3, 4, 5, 6, 7, 8. I'm going to stop there because I don't think I'm going to get past that. And then we need our number of bacteria. I'm going to go by tens here because obviously this number is going to explode. And I want to get to a good level. All right, so here we have our graph. It's labeled to a certain degree. I kind of quit on the x-axis because I don't think I'm going to need more than that. So now let's plot some points. Who's red? So we know that we started with one little bacteria at 0 time. So we'll put a teeny tiny dot that's just barely above the axis here. At 1 minute, that has doubled to 2, which is not a whole lot, still pretty low. 2, we're at 4, so now we're moving up just a little bit. We're just below halfway to 10. Right at 3, we're still under 10, but now we're at 8. 4, right now we're up to 16. 5, we're jumping up to 32. And again, I'm doing my best to kind of guesstimate and line these up. Do not have graph paper here. All right, so we go to 32. Now we're going up to 64. Right, and then we're off the graph after 7. Right, so we'll stop here. So then we can kind of connect our dots here. And this becomes a nice smooth exponential curve. And we can just kind of show that this is going to go way up. All right, so there's our graph. We can see the growth pretty easily. We see that it starts growing very fast. All right. So we've got tree graph, we've got our table, we've got our actual XY graph here, plotting some points. Now, if I want to answer questions about later on in this process, right? Like, okay, how many bacteria will there be at the end of the day? Right, the graph's going to be really big at that point. The table has to go to 24 hours. I may not want to fill the table that much, right? So we want the rule, because if I have the rule, I can put it in a calculator. I can calculate it much faster. Right, so we're going to write our rules here next. First, we'll do the symbolic rule. Right, and we'll just use x and y as our variables. So we'll have y equals, right, our start value, 1, times our rate of change, and x as the exponent. Right. It's important to note that in this case, x is the placeholder for number of hours. Okay. It could be a placeholder for number of minutes. It could be the placeholder for a number of 30-minute time periods. Right. So it's good to to kind of label at this point what your variable is representing. Right? X is the number of hours, right? And Y here actually just represents the number of bacteria. And 1 is that start value. And 2 is the rate of change. Right? The multiplier. Right? Any questions on how I came up with that rule based on the work that we've done? Okay. I'm specifically going into this example and showing each part, even though it seems relatively simple, because it is the most simple kind of exponential function I can have. It's a start value of 1, multiplier of 2. Right? It's kind of the most simple case. These can get much more complex, but this is like the base, the parent function, so to say, that we can use to adapt and change based on their given context. Lastly, we have our now next rule, which will be now times 3 equals next. Right? Starting at uno. And that's it. All right, so based on this context now, we've got all these different representations, which could allow us to answer other questions. We could ask, how many hours will it take for there to be 5,000 bacteria? Right, we have the rule, and we have the graph. We can now answer those types of questions. You know, we can ask in 24 hours, in 1 day, how many bacteria will there be? And we can calculate that. Right? So let's see. Would you guys like to see an example of how to use this formula in that way? Okay. All right, so then back to this one. All right, so we did our example here, bacteria cells. We are now moving on to the concept of what changes now when the rate of change changes. Right? So if we're thinking about our pay it forward example, right? What changes if each person helps 4 people instead of 3? Right, so in our original pay it forward, right, we were helping 3 people. Now what changes when we help 4? So in the tree graph, what changes? We're thinking about that original example to pay it forward. If they're now helping 3 people or 4 people instead of 3, what changes on the tree graph? There are more people, yes. That's correct. So there's more people represented on the tree graph. Right? We're helping 4 instead of 3, so the amount of people is growing. But visually, how would we see that change on the tree graph? Right? If we look back at our tree graph here, started with 1, and that person helped 3 people. Yes, Nicholas, that's correct. The rate of change is now higher. So if this tree graph was to represent 1 person helping 4 people each, what would I have to change? What would I have to add? Right, think of how many branches are coming off of each dot. Yeah, there's going to be an extra dot off of each person, right? Another branch, right? So we would have the 1 person instead of just 3, right? They now each get 4, right? We need to add another branch. To each person. All right, so we're gonna have to add that extra branch. So that's how we can visually see that change from the first example to then changing it to 4 people, right? Then in the rule, right, in the symbolic rule, what changes? Let's make it. So far in the rule, we have this form. Which number changes if the rate of change is changed? A or B? Yes, Jocelyn, B changes, right? B is representing our rate of change. So this changes from 3 to 4, right? We'd have a similar change in the now next rule, if we're doing that one. And we have now times B equals next. Starting at A. Right. And we have the same thing, because I put the letters in the same place, right? that b, the multiplier, changes from 3 to 4, right? Which then, obviously, if we're multiplying by 4 instead of 3, we're going to have way more people, right? The rate of change is higher, so we're going to increase faster, right? But what I want you guys to see is where the rate of change goes in the form. Right? Understanding what these look like, right? Tree graph, the smaller cool. The graph and table follow once we understand what the rate of change is impacting, right? For these things, the rate of change is always going to be attached to that variable, right? Just like in a, the rate of change is attached to that x variable, right? In this case as well, the rate of change is attached to that x exponent. All right, a, while it's still being multiplied, is the start value. It does not have the exponent. Okay. Any questions about this? Anything I can clarify? Okay. So lastly, what changes in the representations when the start value changes? So it's considered the same two things. The tree graph, right? And in this case, we're thinking about our bacteria example. So if I'm changing from 1 bacteria to 5 bacteria, how do I need to start my tree graph? Am I adding branches to the first dot, or am I adding more dots to the first level, to that level 0? Yes, we're going to add more dots, right? So the changing the start value adds more dots to the beginning, right? Changing the rate of change adds more branches to each dot. Okay. So in this case, rather than just having the 1 dot, it would start with the 5 dots, and each of those would still carry that same doubling rate of change. Right, and we could see just off of one level that this is going to grow really fast at this point because we're starting with 5 instead of 1. The numbers are going to get bigger faster. Right. And then in the rules, why it keeps jumping like that? In the rules, where do we see this change in the start value? We have the same representations as before, right? We have our y equals a times b to the x, and we have now times b equals next. Starting at a. Right. When I change the start value, yeah, we're going to see that change in a. Thank you, Jocelyn. This goes from 1 to now be 5. Now, you may be asking, Mr. Mosley, why are you spending so much time on this? This being the 3rd year in a row that I've taught Math 1, this is the most common type of error that I see, is that it's not that students don't see what's going on, it's that they represent it incorrectly, right? and they put the 5 in where the b is supposed to be, or they put the start value as the exponent, or the multiplier as the exponent, and the start value is b, and they completely leave out the actual start value, right? So I'm taking the time to make sure that we understand what are the parts of the rules, where do they show up in our tree graph, how are they used in a table, right? The labeling and understanding of what the representations are makes it so you can have access to the rest of the math, right? You can now solve problems. You can dissect a word problem and put things in the right places. That's incredibly important. That's a bigger skill than just being able to multiply and divide and use an exponent. Okay. All right. What questions do you have? No? Okay. I'm gonna end our slideshow because that's the last slide. I'm going to jump back into Canvas. So we're going to look at our discussion. All right. So this is our discussion board. It's the bacteria are spreading. And this seems really tiny. All right. So we'll zoom in here a little bit. All right, so suppose a single bacteria cell lands in a cut on your hand and it begins to spread by growing and doubling every 20 minutes. All right, so you've been provided with the rate of change, right, a start value, and a time period. All right, so if we look at the table here, each number represents how many 20-minute time periods have passed, right, which means the value of your exponent tells you how many 20-minute time periods there have been, because that's how often you're multiplying. Okay, so when you write your rules, especially the symbolic rule, keep in mind that the exponent is representing number of 20-minute time periods, not just an hour or a day, because in the future you will be asked, given this type of circumstance, how many bacteria will there be in 3 hours? And the number one mistake is someone was going to use 3 as the exponent value, right? Instead of saying, okay, well, there's 3 20-minute time periods in 1 hour, so in 3 hours there's 9 20-minute time periods, so I need to use the exponent value of 9 for this scenario, right? In this case, I'm not asking you to calculate with the symbolic rule. I want you to find the symbolic rule, the now next rule, and complete the table. That's the entirety of the task. All right. So in completing this table, what you can do when you go to reply is put in a table. Right? You can actually just recreate the table as closely as you want. You'd need a 10 by 2 table, right? In which case the first 2 left-hand side boxes would be the name of each row of the table. Right? So you can add a table right here in the text editor, fill it in, and then to write your symbolic rule to make it actually look nice and mathy, you can also insert an equation. And it pops up this little equation editor that makes things look nice. And so you can actually make it be nice and pretty, right? If you hit superscript here, it'll give you that little exponent guy, right? And so you can type up something that looks like a nice math equation if you like. You just go boom, insert, there it is. You can make it bigger, you can make it smaller, right? So there's that option as well if you want to type up a nice looking equation. Otherwise, you can just use the text editor, in which case you have a superscript button right here as well. So you can get the exponent. If you submit your answer just as something that looks like this, that is incorrect. You have not represented an exponent. you need to have the superscript for the exponent. Okay.